of design using state space representation when we were talking specifically about the concept of pole placement. I did not complete that because it was just an 1 hour class. However, today I intend to sort of recap what we did in the previous class, and then we carry on with the 3 methods of solving or attempting to solve the control law, as it were. So today's class is going to be a little bit comprehensive, but that is for your own sake, and also just to end the class, I'll probably give you a few highlights regarding the exam before we close. All right, so to begin with, let me share my screen, and then we proceed with what we was doing in the previous class. So just give me a minute. All right. Please, during the study or during our class, if I don't have a connection, because I'm still very far from Nairobi, so if I don't have a connection, or if the connection is lost, or if you can't hear me, please just notify me so that I can rectify that, because it's very important that our class is seamless. All right, good. So in the previous class, like I mentioned, for those who are able to attend, we introduced the concept of doing design using state space representation. Remember, the idea for learning some of these skills is so that we are able to design control systems on our own. Just like we did root locus, we were able to design a lead compensator, a lag compensator, and a combination of the lead and lag compensator. So the same way, because we learned about the state space representation, which is the representation that is used mostly in digital systems, it is important that we know how to carry out design using the state space representation method. And the most common method is what we're calling the pole placement method. Please remember, in the concept of doing design in control systems, usually we have either to play around with the gain of the system, or alternatively play around with the location of the poles. That way we are able to either control the stability of the system or the transient response of the system, meaning we can play around with the rise time, with the maximum overshoot, with the settling time, with the steady state error, and all that. So it is important for us to understand that the concept of designing control systems usually targets the gain of the system or the location of the pole of the system, because that determines the stability of that control system. So here we are on the concept of pole placement. Just to remind you, for those who, and please consider this also as a revision, for those who have forgotten the main equations that represent state space, we have 2 main equations, and that is, 1, we consider x bar equal to ax, or x derivative, plus bu, and the output y equals to cx plus du. Please note that these are matrices for the uppercase and vectors for the lowercase. So this is the equation that, or these are the 2 equations that usually guide our state space representation. We defined both the matrices and the vectors. I do not want to go into that, but as long as you know that this is the state equation, this is our state equation, and then this becomes the output equation. Okay, so usually it is important for us, actually I would say state equations, because if you write them out, it will always be more than 1. And then the output equation is usually just 1 equation. So in the previous class, if you remember, just to recap what we did, we said we can represent these state space equations into a block diagram. If we start with the first one, you can see that the output is a derivative of x, and it's a summation of the product of a and x, b and u. So if we have, so I can start with the summation. I think we did this in the previous class, but I'll just repeat it for your sake. Now, if you have x here. Let's say we have the x derivative here. For us to make it x, we have to integrate it because it's a derivative. So if we integrate that, then we obtain x. Okay? So then that x, we can multiply it with a. Okay? So we can multiply that x with the a, and then we add it. So this could be plus. Okay? So you can see we have ax, so plus bu. So we must have b, and u is the input, of course. So that is u. We did this in the previous class, but it has to be a summation. This is a plus, this is a plus. Please note it's a positive feedback. It's not negative feedback, because if it's negative feedback, then here it would have been ax minus bu. So we have that the derivative of x equals to ax plus bu. Then the second equation is y equals to cx. Y equals to cx. So we already have x here. We can just multiply it with a c. We can multiply it with a c. So we already have cx. Because we have cx, let's look for du. So that means we have to take u and multiply it with a d. So we have to put d matrix d here. Okay. And then so we have du, and then we have to sum them up. So there's a summation that joins these two again. There's a summation here. And so this I can put as a plus and also a plus. That's a summation. So we have cx plus du, and that gives us y. So that gives us the output here, y. So basically, this is the equivalent block diagram that represents our state space representation. It's a very, very important one. However, remember, our idea here is to introduce a design criteria. You see, this is typically how we represent control systems in state space. So this is the equivalent block diagram. But how then can we introduce the concept of pole placement so that we use it? Because if we have a provision for placing a pole, that means we can add a pole into the system, then we can play around with the characteristic equation, or we can be able to change the stability of the system by being able to adjust the pole location. So to do that, it has been done before, and so this is just a principle that we have to learn. The best way is to introduce a feedback. I'm drawing it using dots because it's not part of the original system. It's part of the design. This is part of the design itself. So you introduce a feedback with a minus k. We'll look at what that represents later, and we feed it back to the input. Okay? So that's fed back to the input like that. Okay? Please note, I'm very, very specific and deliberate on the direction or the arrows, on the arrows that I use and their direction. It's very, very important. So if you look at the dotted part of the diagram, you can see that we can draw an equation, another equation. Aside from what we already have as the state space representation, we can also have another equation here, which is clearly u equals to minus kx. U equals to minus kx. Now, for those who remember, we said that this is what we are calling the control law expression. This is the control law expression. The control law expression, a very, very important expression indeed. The control law expression. Okay? So we'll see how we make use of this control law expression to carry out design in different areas. We'll do an example. Now, please note that the uppercase letters here are matrices. We defined them in our previous classes. But what I want you to remember is the matrix A this matrix here is a very, very important matrix, the state matrix, because it is the one that helps us to obtain the characteristic equation of the transfer function. Remember, we said that we human beings or designers are able to interpret a system when it is represented in the transfer function form. But when it's written in the state space representation form, we cannot easily interpret it. Computers will easily interpret state space representation. But human beings are used to transfer function because it gives a direct correlation between the input and the output. So I can tell the number of zeros, I can tell the number of poles. I can quickly tell whether the system is stable or not, because transfer function is a quick way that we human beings are able to interpret. So the A matrix, I would say this one helps to obtain the characteristic equation. The characteristic equation. It's a very, very important matrix, and you'll see that in our analysis today of the transfer function. Okay? Hence, because of that, because of the A matrix, we can establish, we can establish the pole location. We can establish the pole location of the control system. So that's how important the A matrix is, control system. And because we are able to determine the control location of the control system, then it means, because we are able to determine the pole location, we can now know whether the system is stable or not. Okay? Consequently, we can determine whether the system is stable or not. So I don't intend to write a lot of notes today. I simply intend to show you how we use some of these principles. Okay? Now, because remember, the original diagram, the block diagram without the dotted section, is the typical representation of a state space. However, our design introduces the dotted section. And if the design introduces the dotted section, then our equation changes. Remember, look at the state equation. The derivative of x equals to ax plus bu. But now we have introduced a different concept in our design. So because we have introduced it, we need to consider it in our state representation. What that simply means is we now need to substitute for the value of u in the state equation. So the state equation is x equals to the derivative of x equals to ax plus bu. But we have just seen that u itself is minus kx. So if we substitute that, then we now have the derivative of x would be equal to ax minus bkx, because u is minus kx. So I'm simply substituting for u. We can quickly write this because we have a common term on both sides. So we can have a minus bk over, in brackets, x. So clearly, if you compare these two equations, you can see that these two equations, so we can see that A, the matrix A, the one that I told you was very, very important in establishing the characteristic equation, that matrix A has been transformed into A minus BK, just by observation. We can see that where we had the matrix A is now replaced by A minus BK, because A was the coefficient of X, the state variables or the state vector, okay? A was the coefficient of X. But now, in the second part, where there's the design element, where we have introduced the dotted part, Now you can see that the coefficient of the state variable, so the state vector, is A minus BK. Okay? That is the control law expression. Now, typically, this is just the normal case, again, without the design or without the dotted part. We can typically, the characteristic equation, and for those who have been revising, you must have seen this in the notes. The characteristic equation is usually given by SI minus A, then you get the determinant and you equate to 0. Meaning, if you want to determine the characteristic equation of a state space representation, all you need is the matrix A. Then you have SI, and I is an identity matrix. So you have SI minus A, you get the determinant, then you equate it to 0. That gives you the characteristic equation. But now, in our design, things have changed. In our design, okay, we have transformed the characteristic equation, meaning what we had as SI minus A is now transformed into something else. Remember, it is now, that you can see it, A has changed to A minus BK. Remember, we said originally the coefficient of X was A, but now the coefficient of X is A minus BK. Therefore, we say that we have SI minus A, but A has been transformed. Now in the design element, okay, in the pole placement design, we now don't have A, we have A minus BK. So I'll have to write that it is now A minus BK. So this is the determinant now, okay? And we equate that to 0 in order to get the characteristic equation. So we can actually say that the new characteristic equation, is now SI minus A plus BK. Notice I have just opened the brackets. You get the determinant and you equate to 0. So typically, without a design, using the typical state space representation, we usually get the characteristic equation using this method. Okay? So, for example, let's say if A was 0, 2, minus 1, 3, something like that. So you'll have SI minus A determinant should be the same as SI means, because we have a 2 by 2 matrix here, you'll be having S0, 0S, meaning we have just taken, let me make it clear. It's like saying S into 1, 0, 0, 1, okay? So this is the identity matrix, and this is the S, okay? So having said that, it is important for us to understand, therefore, that in our representation, we can have, in this case, and this is just an example I'm giving, you have now minus A, which is 0, 2, minus 1, 3, okay? So once you have it like this, you get the determinant, you equate to 0, then that gives you a characteristic equation. So you'll have something like S squared plus blah, 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 minus sum equals to 0, okay? That is the characteristic equation. Anyway, so we'll get to use that quite a lot later. What I want us to remember is that now, because this is a design, we have changed the way we obtain the characteristic equation. Now we don't have it as SI minus A. We now have it as SI minus A minus BK, which is basically now SI minus A plus BK, if you open the brackets out, okay? So this is what we discussed in the previous class. For those who never attended, you probably now are up to speed with what we did, okay? So what I want us to do, which is now very critical, is how do we actually solve this? How do you solve the control law? How do you solve this, okay? And by solving this, we basically saying, how do you determine the new characteristic equation? Remember, ladies and gentlemen, if you have the characteristic equation of a control system, you can tell what the roots of that characteristic equation are. Those are actually the location of the closed loop poles. And because you now know the closed loop poles, you can tell whether that system is stable or not. Okay, so that's why it's a very, very critical concept. Now, when I concluded the class, the 1 hour class, we said that there are basically 3 methods for solving, or 3 methods of solving the control law. 3 methods of solving the control law. So the basis of my class today is to quickly show you the 3 methods. The first one that we mentioned was called the matching, my marker is misbehaving, the matching coefficient method. Very, very important method, the matching coefficient method. The second method is known as the Ackermann's. I think we listed this in the previous class, the Ackermann's method. And lastly, the third method for solving this control law is the transformation method. The transformation method. Very, very important. So now, what I want to do is to show you how each of these methods are used to solve the control law. So I'll basically give one example and solve them using these 3 methods and see if we can obtain the same solution. Okay, and then later I will probably ask you to figure out why and where do we prefer one method over the other. That would be left for you to discuss. Okay, so let's start with the matching coefficient method. Okay, this is the first one. Basically, once I'm done with solving this, then we are done with the class. The matching coefficient method. Coefficient. Sorry, my marker is misbehaving today. The matching coefficient method. So let's solve a question, because it's usually important that I illustrate this using an example. So the question is this. Design, remember, these methods are used in design using pole placement. Design a state space, let me just say, design a state feedback controller. Design a state feedback controller to get the pole location, because that is very important, obtaining the location of the pole. That's why it's called pole placement. To get the pole location, at -1 plus or minus J2 for the model. Now that model is represented as the derivative of x equals to 0, 1, minus 2, minus 3. This is a simple example because it's a 2 by 2, but we can always transition to a 3 by 3. The same principles apply. It's only that now the matrix order changes. So we have, so you're given a state representation. That is the state equation and the output equation. So that is our model. But you're told, can you design a state feedback controller so that we get the pole location at -1 plus or minus J2? So you are trying to change the location of the poles to be at -1 plus or minus J2. Now, remember, we are calling it a state feedback controller because you can see from our representation here that the control law is a feedback system. We are feeding back the -k into the input. So that's why it's a feedback controller. So some books will actually, you will see if you read Ogata, for example, they call it pole placement via feedback controller because you're using the feedback to place a pole into your control system so that you obtain the desired expression that you want. Okay, let's go back to our example and see how we can solve it using the matching coefficient method, the first method. Now, ladies and gentlemen, by now we all know, and it should not be new to anyone, that this is the matrix A, this is the matrix B, And of course, this is the metric C that now everybody knows. Okay. However, in fact, let me just indicate here, note, very, very important. In the case of a feedback controller, like the one we are dealing with now, in the case of a feedback controller, we only need A and B matrices. Okay, so we only need the state matrix, and we also need the second matrix, which is the input matrix B, okay, or the input vector B. Okay, so we only need A and B, not the C matrix, meaning the output equation is not important for us whenever we are dealing with the feedback controller, because it makes sense. If you look at our block diagram, ladies and gentlemen, we have nothing that connects us to the output. The feedback controller connects our state vector X back to the input. So that means we are only interested in the first equation, the state equation. The output equation is not included. It's not important in the feedback controller design. So you can always see that as much as you're given an expression that involves the state equation and the output equation we are never interested in design. We design with the input as our reference, not the output. Okay, good. So now let's look at our solution. Let's solve this now. Let's solve this using the matching. Remember, we are going to solve this same problem using all the techniques or the methods that we have listed. Now, the best way to solve this is to know step by step what we need to do. So here, let's look at the first step. What do we need to do? In step 1, using the matching coefficient method, and this is not just using the matching coefficient method, it's for all methods. You will see that the first step for all methods is to test for controllability. Now, this is why I deliberately taught you controllability and observability before we came into doing design. So for all the methods, the first thing usually is to test for controllability. Why do we need to test for controllability? Because the feedback controller, so let me just indicate it as a note, the feedback controller design, the feedback controller design is only possible if the system, in fact, I should say if and only if. So those who know maths and who've been using some of these symbols, if and only if is just IFF. If and only if the system, is controllable. So please note that whenever you are asked a question to do any design using the feedback controller design method, the first thing usually, whichever method you decide to use, the first step is usually to test whether that system that you are provided with, the model, whether it is controllable or not. Now, for those who have forgotten, this is revision again. How do you determine whether a system is controllable or not? Please remember the control matrix. I think we can, I don't know whether I denoted it as CM, I don't know, but the control matrix was given by B. Notice vector C is not going to appear anywhere in controllability. We are only using vector A and B. Like I indicated, only vector A and B is needed in this design. But anyway, for controllers, for controllability, we have to make sure that you have A squared B all the way to AN minus 1 B. Okay? We have to obtain the controllability matrix. Remember where I think we had said N is the order. N is the order. Other books call it rank of the control system. Okay? In our case, because you can see here the matrix A is a 2 by 2 matrix. Therefore, our system or our control system is of order 2. So I can actually just say for a 2 by 2 matrix, and that is referring to the matrix A, we have n being equal to 2. N is of the second rank. And therefore, your control matrix changes because n is 2. And so the control matrix will just be B and AB. Because an minus 1, if n is 2, then we have AB as the matrix on that column. So you have BAB, okay? That is for a 2 by 2 matrix. So remember, we are testing for controllability of what has been given, our model, okay? So let's see, what is B? Controllability in our case here, the matrix B is what? The matrix B is 0, 1, and the matrix AB is the multiplication of A and B. So it's like saying we have B is 0, 1, and then AB is the multiplication of A and B. So that becomes this multiplied, that's 0, that's 1, 1 and minus 3. So you have 1 and minus 3. 1 and minus 3. Please remember, this can also be a 3 by 3 matrix. That means the rank 3. And if it's the rank 3, then you'll have your B, AB, and A squared B. I think we've done these examples in class, so I'll not engage you there. Let's stick to what we have here today. So now, remember, we are supposed to get the determinant. That's where we test for controllability. We test for controllability by getting the determinant of this control matrix. And the rule is, if the determinant of that control matrix is a non-zero, it's not equal to 0, then the system is controllable. Because the system is already of order 2. The system is already of a rank that is greater than 1. So now, the determinant of our matrix here is given by the determinant of this is 0 minus 1, which is negative 1. I hope you now know how to get the determinant of matrices. I shouldn't get so much into that. So since, remember, you always have to justify at the end when you're testing for controllability and or even observability. Since the determinant of the controllability matrix is not equal to 0, it is negative 1, okay? It is non-zero, then the system is controllable. And let me add, and the controller design, in fact, the feedback controller design is possible. If you find that the matrix is not controllable, if your system is not controllable, then you don't even need to do the design, because the design is only possible if your system is controllable. I indicated that here, that the feedback controller design is only possible if and only if the system is controllable. So we have tested the system that we've been given in this example, and we've seen that clearly that system is controllable because the determinant is minus 1. It is non-zero, okay? Step number 2. Let's now look at the second step. So now that you have determined that your system is controllable, what must we do next? You now need to do what you say, you find the matrix scanner. How do you do that? Very simple. Very simple. We write the equation SI minus A plus BK determinant should be equal to the desired equation. Please remember, notice, I have not cooked that figure. The new characteristic equation was here, SI minus A plus BK. This is the characteristic equation of the design. Without the design, the characteristic equation is obtained by getting the determinant of Si minus A. But with the design, we have the new characteristic equation as Si minus A plus Bk. So for us to be able to design properly, we have to write that our new characteristic equation should be equal to the desired equation. DE is basically desired equation. It's the desired equation. Now, ladies and gentlemen, at this point, I should be able to indicate that the desired equation is simply the desired expression. The desired expression. And sometimes, or some books will call this whole thing the matching coefficient formula. The matching coefficient formula. Please note that whatever I'm discussing with you today is not obtained from any single book. It's just a study of both Ogata, which you know, and then the control system design, Nagrath and Gopal, and so it's just a combination of different books, but it's the concept is what is critical here. So now we have to use the matching coefficient formula. Now, the desired expression, just like in the design when we were using lag compensation and lead compensation, the desired expression is always given in the question. So let me go back to the question to just show you what it said. Design a state feedback controller to get the pole location at -1 plus or minus J2. So the desired location of the poles should be at -1 plus or minus J2. So it means that we'll use -1 plus or minus J2 to obtain the desired expression, because that is what the design wants you to do. All right, now let's go back so that we are not lost in the process. Let's find the left side first. We'll get to the desired expression. So let's find the left side first. So I'll write this for you to understand. Si, please remember, this is how we obtain the characteristic equation of the design feedback controller design. The left side has the characteristic equation, the right side has the desired expression, meaning that the characteristic equation must be equal to the desired expression. So that is the design element. That's why we are calling it the matching coefficient formula. We need to match the characteristic expression of our design to the desired expression, and then we'll be able to obtain our solution. Okay, that is what is critical. Good. So now, ladies and gentlemen, let us see if we can obtain this left-hand side. The left-hand side should be, okay, of course, we have to get the determinant, because the characteristic equation, you must get the determinant. So let's see what the left side is. So the left side is, this is a 2x2 matrix. So it's S0, 0S. I've told you how to obtain that. That is the Si minus A. A from our expression here, A was given, our matrix A was 0, 1 minus 2 minus 3. 0, 1 minus 2 minus 3. So we have 0, 1 minus 2 minus 3. That is the matrix A plus B. I remember B was 0, 1. Okay. And then we have K. So in my K, I will write it here, but then I'll show you why. K1, K2. That is the matrix for the K. And then we get the determinant. Now note, because I know you are wondering, how did I get that? K is the order of the control system. It's like the N of the controllability matrix. It's like the N of the controllability matrix. But now, because here we are dealing with actual characteristic equation, K is the order of the control system. And typically, again, this you'll just notice it by studying. Typically, it is a row. It is always, let me just say, if that would be a repetition. Typically, it is a row matrix. It is a row matrix. You see, like here, I've seen K, I've indicated. So let me put it in red here. This value is K. Remember, this was S minus A plus, this is B, this is matrix B, and that is K. K is typically a row matrix. For those who probably are still confused, let me give you examples. E.g., for order 2, K becomes K1, K2. It's a row matrix. It is a 1 times something. And then for order 3, K would be K1, K2, K3. Okay? K1, K2, K1, K2, K3. Right? So this, and order 4 would be K1, K2, K3, K4. But it's typically a row matrix. So that is how we obtain K. I've indicated it on the equation there, so it should be clear. So you can solve this because this is now easy. So now, when we solve it, what are we going to have? We are going to have, let me solve this. If we solve it now, we'll have, let me just indicate again, S0, 0S. Remember, you have to get the determinant at the end of the day, so don't forget that determinant part. And then the other one was 0, 1, minus 2, minus 3. Okay. Plus, now typically, this is, it's a what? You have a 2 by 1 multiplied by a 1 by 2, the row matrix. So you must get a 2 by 2 matrix. So if you solve that, you should have 0, 0. Yeah, because this multiplied by the upper part is 0, 0 by the downer part, to be K1, K2. So you should have a 2 by 2 matrix, and then you get the determinant.
Excuse me, sir.
Yes, please.
I think for the A matrix, it's positive 3, not negative 3.
Oh, it's positive 3. Let me check again. Our A matrix. No, but our A matrix is 0, 1, minus 2, minus 3 from the equation. Let me check again. 0, 1, minus 2, minus 3. A matrix 0, 1, minus 2, minus 3. Have you checked again? Because the equation says minus 2. Yeah?
It's on my side, I think.
Yeah. It's minus 2, minus 3 from the equation itself. All right. Anyway, thanks for trying to be observant, which is good. Now, let's carry on. If I make a mistake, please just intercept and or interject me, and then let's do the right thing. Okay. So now, because we have indicated in our case our control equation is of order 2, so we don't need K1, K2, K3. We just need K1 and K2. So once we have solved this, remember, we are trying to solve the left-hand side of our matching coefficient formula. The left-hand side contains the characteristic equation, and the right-hand side contains the desired expression, which we'll get to later. So the characteristic equation, if we solve this now, becomes, again, we have to S minus 0 plus 0. That is S. So you have the determinant of a matrix here. Okay. S minus 0 plus 0. That is S. The other one is 0 minus 1. That is negative 1 plus 0. So that is minus 1. Please make sure that I'm correct. If I'm not, you let me know. Okay. I think I'll need to do this. Am I doing it correctly? Okay, yeah, it's correct. This is a determinant. Okay, 0 minus 2, that's 2. 2 plus K1, so this is 2 plus K1. 2 plus K1. The other one is S minus 3, that is S plus 3. S plus 3 plus K2. So this one is S plus 3 plus K2. S plus 3 plus K2. Let me write that properly. S plus, plus 3 plus K2. Okay? S plus 3 plus K2. So we get the determinant of this matrix. Remember, we are still in step 2. We are almost there to the solution, but we are obtaining the characteristic equation, the left-hand side, and then we'll get to the right-hand side in step 3. Now, So if we solve this, what do we get? Getting the determinant of a 2 by 2 matrix is easy. It means this is the same as s squared plus 3s plus 2k2. Or no, let me write it properly. Plus k2s minus 2 minus k1. No, not minus, because it's this. It should be plus k plus 2 plus k1. Yeah. Please check me so that I don't mislead you. So this is s squared plus 3 plus k2s, I think. Yes. Plus 2 plus k1, like that. Good. So this is basically this is the characteristic equation. This is our characteristic equation. Characteristic equation. Of course, we can equate it to 0, but our matching coefficient formula requires us we equate it to the desired expression. We don't equate it to 0, we equate it to the desired expression. So that means that takes me to step number 3. Step number 3, where we have to now obtain because it's a matching coefficient. So once we get the characteristic equation, we get the desired expression, then we match their coefficients. That's the solution. So find the desired expression. Find the desired expression or equation, whichever, what we are calling or abbreviating DE. Okay? How do you get that? The desired expression is always obtained, it's becoming so thick, is always obtained, make it 20, somewhere, is always obtained from the pole location, from the pole location. Now, please remember our pole location. What's happening? I'm having a very, okay. The pole location is, our pole location is, my marker is misbehaving now. The pole location is S equals to -1. Remember, we had said plus or minus J2. Please, from the equation. It's not my thing. It's from the equation itself. Let me check again so that I don't. Yes, -1 plus or minus J2. That is the desired pole location. The desired pole location. So now we have S equals to plus or minus J2. Of course, ladies and gentlemen, we know this is like saying you have S equals to -1 plus J2, and you have S equals to -1 minus J2. That's what it simply means. Now, these two, it's just like indicating, if I was to write them down, these two poles, because you can see that there's a complex pole, they're complex conjugate. So you have that, and then you have S plus 1 minus J2. So you have them like that. Now, my maths, I don't know, we used to call it a sum of two squares, something like that. We have A plus B and A minus B. Remember, if you're looking at it, A is like S plus 1 and B is like J2. So if you are to solve this mathematically, you were told is A squared minus B squared. So if I simply just get A squared minus B squared, it's like saying S plus 1 squared minus B is J2. So J2 squared. So if I solve this is S squared plus 2S plus 1. So S squared plus 2S plus 1. Then J2, remember, if I square J, I get a negative. So that negative is going to make this negative a positive. So it should be plus 4. So this is basically S squared plus 2S plus 5. Anyway, you can do whichever way you want to solve it. I just saw that as a quick way. So therefore, our desired expression, because now it's the pole location. We've told you the desired location is obtained from the pole location. And we have two poles here. So you simply multiply them out. And if multiplied out, then you obtain, so let me say, therefore our desired expression is simply s squared plus 2s plus 5. And then lastly, our last step now, because this is why we are calling it the matching coefficient, using a different notation. This is why we are calling it a matching coefficient method. The matching coefficient method is SI minus A plus BK from our diagram originally, get the magnitude, then you equate it to the desired expression. We have just obtained our characteristic equation as s squared plus, let me see that again, 3 plus k2. So we have 3 plus k2s plus 2 plus k1. And then we equate it to our expression here in step number 3. And our expression in step number 3 is s squared plus 2s plus 5. Okay? So once we have it like that, then now it means that we can match the coefficients on left-hand side. And so let me just say equating coefficients of s and constant on both sides. Clearly we can see 1, that is the coefficient of s squared, and then the 3 plus k2 should be equal to 2, and therefore k2 should be equal to minus 1. Yes, because it's 2 minus 3. Then 2 plus k1 should be equal to 5, and therefore k1 equals to 3. And therefore, remember our last step. This is last step. Step 5. So in step 5, what is k? Because remember, the question requires us to obtain the value of k. So k, because this is a second, we had said this is order 2, k, order 2, k equals to k1. It's a row matrix, k1, k2. And therefore, we can say k equals to, what is k1? It is 3. K2 is minus 1. Okay? So this is basically the design, obtaining the k. So this becomes our solution using matching coefficients. Because it's called matching coefficients because we obtained the design characteristic equation on the left-hand side and the desired expression on the right-hand side. Then we equate their coefficients. Okay? Now, the characteristic equation, which is on the left side, is obtained from our diagram. You can see our design diagram as indicated. We introduced the concept of the control law expression. We introduced the minus kx equals to u, this one. So that is why we have the characteristic equation with this dotted expression included on the left-hand side, and then the desired expression, we obtain it from the expression that is expected or that is desired in our design. So we equate those coefficients and then you obtain your solution. So that basically means that we have obtained the value of k. Notice k is not a constant, ladies and gentlemen. K here, you can see we have indicated that k is minus 3. I think it's minus, no, it's plus 3. I think it's plus 3. Yeah, 3 minus 1. So it's a vector, just like A is a vector, B is a vector, C is a vector, D is a vector. So here K is also a row vector in this case, or a row matrix, whatever you want to call it, because for higher order it can turn out to be a matrix. Okay, so please note that that is basically the design, solving the control law expression. So if I were to, in my design, all I have to do is I have made a design such that I have obtained the value of k. So what I have to do is I know that I simply feed back this value of k to the back to my input for me to obtain the required state vector or the required expression that I want. Okay? So that is part 1. So we go to part 2, which is solving this now using the second method. I hope that's very clear. Now, the second method how much time do I have? Should take me about 10 minutes. Yeah, we'll be finishing in good time. The second method is known as the Ackermann's method. Please note, we have the Ackermann's method. I'm simply going to use the exact same expression, the same question, the Ackermann's method. Let's solve this using the Ackermann's method and see if we obtain the same solution. Okay. Now, the Ackermann's method, unlike the matching coefficient method, comes with an expression that you need for K. You see, for matching coefficient, we said all you have to do is obtain the expression S minus A plus BK, get the determinant, equate it to the desired expression on the other side. So this is the matching coefficient formula. So the Ackermann's method also has its formula, and the formula is given by K. Please note that the design is simply obtaining that vector or the row vector K. That is the design. That's the whole essence of doing design, because it's the only thing that we have introduced in our block diagram. Everything else was there, obtained from the state space representation. But K has been introduced as a feedback controller. So that's why we are calling it pole placement using feedback controller design. So we have introduced a feedback controller. That feedback controller has the row matrix K. Once you obtain K, you have completed the design. So K equals to, this is according to the Ackermann's method. Of course, makes sense. The guy who came up with this method, he was known as Ackermann. So now his method dictates that to obtain design using the Ackermann's method, you must have this expression. And this expression is for two state space variables. Two state space variables. What we are calling second order, or second order. Okay, and K equals to 0, 0, 1 CM, which is the controller matrix, inverse phi of A. Let me actually write phi of A. So you can see the matrix A is the one we are using here again. So that is state 3 state space variables. This is for 3 state space variables, or what we are calling the third order. Okay. So for him, or for Ackermann's method, to obtain K, this is how we obtain K. This is when we are using a 2 by 2 matrix, and this is when we are using a 3 by 3 matrix. Okay. Now, please note that in our case, our example is a 2 by 2 matrix. So how do we solve this using Ackermann's method? Somebody should tell me what step 1 is. Step 1. I told you, whichever method you use, the first step is to do what? To test for controllability. Because if you don't test for controllability, you will not know whether the system needs that feedback controller design or not. Because the feedback controller design works only if the system is controllable. But because we have done the test for controllability in the previous example, I won't repeat it here. But if you are asked to do it using Ackermann's method, you'll need to test for controllability. So let me just indicate here, done in previous example. The first step is exactly the same. And we obtained CM, that is a controllability matrix. Then we got its determinant, and we found that the determinant was, remember, we had indicated that the determinant of CM was, I think it was -1. And because that is not equal to 0, the system is controllable. Okay, we concluded that the system is controllable, and therefore we can design it using the feedback controller design. Okay, that was step number 1. I won't repeat it because of time. Let's do step number 2 of the Ackermann's. Step number 2 of the Ackermann's method. It's clear. You have 0, 1. Then you have the controllability matrix. You're supposed to get its inverse. So the second step is simply to obtain the inverse of the controllability matrix, because it's indicated here. You want to obtain, this is the formula we are using. So you need to obtain the controllability matrix and get its inverse. And because this is a 2 by 2, inverse should be easy. I think it's the controllability matrix was 0, 1 minus, sorry, 0, 1. I don't want to make a mistake. 0, 1. What was our controllability matrix? Controllability matrix 0, 1, 1 minus 3. So, sorry for the scrolling, 0, 1, 1 minus 3. So if that was the controllability matrix, I know by now any student who's worth their salt should be able to find the inverse easily. The inverse of this matrix would be 1 over the determinant. So the determinant here is, we had obtained it as minus 1. So 1 over minus 1. And then elements in the leading diagonal are interchanged. So I think minus 3, 0. And then we change the sign of the elements in the lagging diagonal. So that is minus 1, minus 1. And so we solve this. That's simply minus 1. So you come up with the inverse, therefore, becomes 3, 1. I think that's correct. 1, 0. Good. So this is the inverse of that matrix. 3, 1, 1, 0. So step number 3. Step number 3, you can obtain the inverse the best way you know how. Kramer's rule, I don't know, so many methods that exist. You just make sure you obtain the correct inverse of the matrix. Whether it's a 2 by 2 or a 3 by 3, just obtain the inverse. So if you look at our Ackermann's method, we already have this matrix 0, 1. We already have obtained what the inverse of the controllability matrix is. So we need to obtain phi of A. Phi of A. So I know this is, let me just write, we need to obtain phi of A. And I know students are wondering, how do you get this and what is this phi of A? A matrix, we have it. So how do we get this? We find this. So this is found from the desired expression. Desired expression. Obtained from the desired expression. How is it obtained from the desired expression? Look at this. Phi of S, if I make S equal to, if I transform S to A, becomes phi of A. So I can get phi of S. I'll tell you how to do that. Don't worry. It's the desired expression. But once I get phi of S, I simply change the S to A. I transform the S to A so that then gives me phi of A. Okay? Please remember that the pole location was S equals to minus 1 plus or minus J2. Okay? And we had even obtained the desired expression from there. The desired expression was obtained as what? From the previous example. If you S squared plus 2S plus 5. So you already know how to obtain it. I've indicated it here. So S squared plus 2S plus 5. So the desired expression from the previous example, S squared plus 2S plus 5. But you know how to get it. I'm only trying to save time because there's no need of doing it over and over again when we already did it previously. So therefore, this, because we've said, please note that phi of S is the same as the desired expression, which is the same as S squared plus 2S plus 5. So the phi of S is simply saying, in another word, desired expression. It's just like the matching coefficient method simply calls it the desired expression. Ackermann wanted to use a different expression for it. And so instead of calling it desired expression, he called it phi of S. Okay? So it's just a way of somebody trying to make his work look original. So he calls it a different notation but we know it is simply the desired expression. But notice that the formula has its expression as phi of A. meaning you simply substitute the S for A. So it means, therefore, that phi of A would simply be equal to A squared plus 2A plus 5. Please pay attention. This is the most important part of the Ackermann's method. And this is where students would probably make huge mistakes. Look at this. S is a complex number. That's why we are getting S squared plus 2S plus 5. So S is understood as a complex number, A plus JB, the real part and the imaginary part. However, A, if you remember, is a state matrix. So this is a matrix. A is simply a matrix. Now we are transforming phi of S, which we have obtained from the desired expression, into phi of A. So please note, this is very, very important, and students should not make these mistakes. Otherwise, people will question your integrity as far as being a final year student is. This is a matrix. Please note that. So therefore, this is a matrix. Now, for those who've manipulated matrix, you can't add a matrix and a constant. I can add matrix A squared plus matrix 2A, but I can't add it to 5, meaning I can't say 1, 0, 4, 5, 4 added to 5. This doesn't make sense. This is a single element matrix. So we cannot sum them up. They must be of the same order. So how do we ensure that we add a matrix to a single element? What do we do to add a matrix to a single element? Anyone? You can get a free lunch.
Multiply by identity matrix.
Very good. Thank you very much. That's brilliant. Ogola, thank you very much. So you multiply, so I owe you lunch, remind me. You have to add, you multiply your single element to an identity matrix. Thank you. So therefore, our expression should not just be 5, it should be 5. It should be 5i. Okay? Should be 5i. So that now makes it easy to manipulate or sum it up. Okay? So therefore, our phi of A should be equal to A was 0, 1, minus 2, minus 3. I remember that. So we square it. That means we have to 0, 1, minus 2, minus 3. So that's A squared now. And then plus 2A. So you have 2 into 0, 1, minus 2, minus 3. Okay? That is the 2A part. Plus, now 5i. Identity matrix. Like that. So then now we can solve for this. Solve for this. So you multiply, sum that, and sum that. Okay? Do that, and we obtain 3 minus 1, 2, and 2. Do your manipulation the best way you know how. I think that is it. 3. Let me just confirm. 0, 0. That's 0, 2. Yeah, so 3 minus 1, 2, and 2. So this is our phi of A. And so we complete this step, which is step number 4. All these steps are usually just about 4 steps. So step number 4 is now finding the K. Finding K. Find K. And the K is given in the Ackermann expression. Please remember the Ackermann expression. Let me write it again. Let me see it. K. I just indicated what Ackermann's. Okay, 0, 1, the inverse, and then phi of A. So the Ackermann expression states that for a 2 by 2 matrix, we have 0, 1, and then you get the inverse of the controllability matrix, and then you multiply it by phi of A. So clearly, you simply substitute, which is the same as 0, 1. The inverse of the matrix, if I remember, is 3, 1, 1, 0. It's 3, 1, 1, 0. And then phi of A, 3 minus 1, 2, 2. And you simply do your matrix manipulation, and therefore K becomes 3 minus 1, which is exactly the set that we used. Sorry about that. So it is exactly the same thing that we obtained when we used the matching coefficient method. So these two methods can be used and use any method. But please remember the rules of each method. Each one of them has about 4 steps. Just know that. Now, ladies and gentlemen, let me conclude with the last step, the last one, which is also quite easy, and then we wrap up the class. So the last method for doing this kind of design is known as the transformation method. Transformation method. Transformation method. So just like Ackermann, the transformation method also has its formula. You must know its formula. So for the transformation method, the formula is K equals to alpha 2 minus A2, alpha 1 minus A1, inverse of T. Now, T is given by the controllability matrix multiplied by W. So let me just indicate where. This is the controller matrix, or we call, some books call it controllability matrix. Okay, and W is given by, for the transformation method, W is given by A1, 1, 1, 0. Okay, and so somebody would ask, I see alphas, alpha 1, alpha 2 in the value of K. How do you obtain the alpha? So the alphas are found from the desired expression, which you now know how to obtain. Now, the desired expression, how do you obtain it? You obtain it the way we do, but then you equate it to be S squared plus alpha 1 S plus alpha 2. So that's how you obtain alpha 1 and alpha 2. Okay? And A1 and A2. So how do you obtain the A's? The A's are found from, very, very important, let me write it in capital, from basic characteristic equation. Not the design characteristic equation, from the basic characteristic equation. Remember, the basic characteristic equation was SI minus A determinant equals to 0, not the design characteristic equation. So therefore, what we simply mean is you have SI minus A determinant should be equal to S squared plus A1S plus A2, and you equate that to 0. You should be able to do that. We'll do the example and you'll see. So note, this we have done. You can see that this formula, the formula that I've indicated here, formula is only applicable, this formula is only applicable for two state variables, two state space variables. You can do it for a 3-state variable. For 3-state variables, it changes. Okay, let me write it in red for you to remember. For 3-state variables, K would be equal to alpha 3 minus A3, alpha 2 minus A2, alpha 1 minus A1, T inverse. T is what I have indicated, but for a 3, of course, the controllability matrix remains, but it will be a 3 by 3 matrix. So W needs to change also. So W would be A2, A1, 1, and A1, 1, 0, and 1, 0, 0. So this, for a 3 by 3 matrix, you'll have it as that. For a 3 by 3 matrix, your DE would be S cubed plus alpha 1 S squared plus alpha 2 S plus alpha 3. And the A's would be obtained from the basic characteristic equation, which for a 3 by 3, the basic characteristic equation would be S cubed plus A1S squared plus A2S plus A3. Okay? And then you equate it to 0. Okay? Yeah. So basically that is for 3 by 3 or your controller of order 3. Okay? So you use a similar. So the formulas are the same depending on which order. Now, however, let's solve this now quickly, just 5 minutes. Step number 1. Step number 1, I cannot overemphasize, test. For what? For controllability. Meaning you have to obtain the controllability matrix and check whether its determinant is non-zero. So this we have done. So again, I am not doing that. You now know how to check for that. Step number 2. Again, just 4 steps, maybe more. Step number 2 is we need to find the alphas. This is the transformation method. Find alphas. Meaning, by the way, it's just called transformation method because we are transforming the K into alphas and A's. These are just constants that this guy came up with. Okay, so find alphas. That is step number 2. But how do we obtain alphas from the equation? Alphas are found from the desired expression. And again, we had obtained the desired expression. The desired expression are found from the pole location. Okay, so now the desired expression, we had obtained it as S squared plus 2S, I think it's plus 5, yes, plus 5. But now we have to equate it to our alphas, which is S squared plus alpha 1S plus alpha 2. So S squared plus alpha 1S plus alpha 2. So that therefore means that alpha 1 equals to 2 and alpha 2 equals to 5. Simple as that. Step number 3. Step number 3 is now we find the A's. We've already found the alphas. Let's find the A's. How do we obtain the A's? It's indicated here from the basic characteristic equation. The A's are obtained from the basic characteristic equation. What's our basic characteristic equation? It's SI minus A. Then we get the determinant. That means we get the determinant of S0, 0S. That's SI minus A. A was 0, 1, minus 2, minus 3. Like that. You get the determinant. So this is just like saying, let's get the determinant of, that is S, that is minus 1, that is 2, and that is S plus 3. Okay? And so this is like saying S squared plus 3S plus 2. And then, so that's, and then we equate it to A's. A's are what here? A's for a 2 by 2, A1S plus A2. So easy. S squared plus A1S plus A2. So therefore, from here, A1 is simply 3 and A2 equals to 2. A2 equals to 2. So we found the alphas, we found the A's. The alphas we found from the desired expression, the A's we found from the basic characteristic equation, not the design characteristic equation. Please don't confuse that. Step number 4, almost there, we find T. We find T. Please remember we had said T is given by the controllability matrix multiplied by W. So therefore T is the controllability matrix. I remember this we did 0, 1, 1 minus 3. We already found that. W is indicated here. W for a 2 by 2 should be A1, 1, 1, 0. What is A1? A1 is 3. So we are having 3, 1, 1, 0. 3, 1, 1, 0. You solve this, you get, this is 0, 1. So you have 1, 0. And the other one is 1. So 0, 1, like that. So you can see there's a lot of matrix manipulation. And by the way, I've just seen that. You can see that this is an identity matrix. That's an identity matrix. Step 5. Step 5 is now, let's get K. Please remember, we had indicated that K using the transformation method is, especially for a 2 by 2, alpha 2 minus A2. Alpha 1 minus A1. Then you multiply it by the inverse of T. That's what we indicated. But now, K therefore would be alpha 2 was 5 minus A2. A2 was what? 2. A2 is 2. Higher. The other one, alpha 1 was 2, I think. Alpha 1 is 2, yes. The other one is 3. So 2 minus 3. Like that. T, ladies and gentlemen, T is an identity matrix. The inverse of an identity matrix is still an identity. And identity matrix multiplied by another matrix is the same matrix. So we don't need to indicate this. This is an identity matrix. So it's just the same thing. Nothing changes there. And so K therefore becomes 5 minus 2 is 3. 2 minus this is minus 1. Okay, so you can actually see that we have also obtained exactly the same expression here. We have exactly the same expression as the previous examples. Okay, now a student would ask, why do we have the 3 methods? Why didn't we just settle on one method and use it to solve for or design for feedback control design systems? Now, I can give you a hint and indicate that there are certain instances where one method is preferable to other methods. Now, I'll leave it to you as a student to go and study and understand where would you apply, for example, the matching coefficient method over the Ackermann's method, or where would you apply the Ackermann's over the transformation method. So which cases are suitable for, because you're going to be designing your systems using these methods. So what would inform your choice of whichever method you pick? You need to do that on your own. You need to study and understand which method should I use in the pole placement design using the feedback controller. Do I need to use the matching coefficient? And why? Do I need to use the Ackermann's and why? Or do I need to use the transformation method? Remember, however, that all the methods will lead you to the same solution. However, there are instances where one method is preferred over the other. And you'll typically understand, I don't want to give it away, but you'll typically understand it's based on the desired expression. Certain times, and also the model. So sometimes the state equation is of a certain order, maybe order 3. You will notice that when you have state equations of order 3, the Ackermann's method is better than the matching coefficient method. Let me leave it at that. I'll not go beyond that. So please figure out why each method is preferred over the other and in what instances. So ladies and gentlemen, that marks the end of our design using the state space representation technique. So we have done root locus, and then we did our design using root locus technique, where we applied both the lead and the lag compensation. We have now done state space representation and seen how we can use 3 different techniques to do design using the pole placement method. Please remember, as engineers, when we do design of control systems, we focus on either playing around or trying to change the values of the gain of our system or the whole location of our system. We never change the plant system. The plant system is fixed, whereas the gain and, of course, the pole locations can be played around with to ensure stability and also to ensure the desired transient response. Very, very important. Thank you very much for listening. If there are any questions, please raise them. Please raise them. I'll need to spend just 5 minutes and then we end the class.
I have a question.
Yes, Kasamani.
It's unrelated to what you're teaching, but more to do with the exam. And the question is whether concerning the format of the exam, is question 1 going to be compulsory, or is it going to be optional for all the 4 questions?
Kasamani, you are attending the class listening to this, but you have the exam in mind. I mean, I wasn't teaching you guys for the exam. I was actually teaching you guys to use this knowledge in the industry for those of you who would pursue control systems. But anyway, because you've asked, let me be generous enough to guide you. Before I get there, let me see. Samuel is asking what's the use of the observability matrix, which we also looked at last year. Now, Samuel, that's a good question, because you can see that in our design, we've basically focused on testing for the controllability and not observability. However, if you remember, let me stop sharing because I need to go to the exam. If you remember, we did both controllability and observability in our previous encounter. And if I recall correctly, I gave you areas where we apply or advantages and disadvantages or application areas of the observability, not the observability matrix, but the observability technique, and also for the controllability technique. So I think I need to refer you back to your notes. Please go back to your notes where we were discussing about controllability and observability. I remember very well that I indicated areas where observability is used and areas where the controllability is used. Okay, so if you go back there, you should be able to find the answers to the question you've just asked me, which is where we use observability. Now, again, the other way to understand that properly is to remember why we need to be able to observe our system. So by virtue of our definition, we had indicated what observability means in control systems for us. Like what is controllability? The basic definition is able to give us a clearer picture of what observability is, and also, of course, what controllability is. I also remember I mentioned that controllability and observability are dual concepts. And the duality was also explained in your notes. And because I want you to read, please go back and understand what those two concepts mean. They are very, very important for you. Okay? What does it mean for a system to be controllable? That means we always have an input. That input must be transferred to any state in the system in a finite period of time. Was very, very important. So that means you're able to control your system. You're able to take an input and transfer it to a state. When we say state, remember the state vector. You can transfer it to a state and you can do it in any finite time. What we have just done today, you've seen that we have taken, we've fed back a system back to the input. We've fed back a controller basically back to the input, and we can do that over a finite period of time. That is why we said that we had to test whether the system is controllable, because controllability means we are able to have an input which can transfer to any state or any state variable at any finite period of time. Okay, but for observability was just to tell us if we are able to determine the initial state of the system. You get any plant system or control system, are you able to determine the initial state with the knowledge of the input only? So you have the input, are you able to tell what the initial state of the system was based on the knowledge of the input of your system? And you also have to do that over a finite period of time. You can't do it infinitely. You can only do it over an interval of time. So that's also very, very important. So some of these techniques, actually controllability is used in design. Observability is not used in design, because observability is just to allow you to be able to check whether you can tell what the initial state of your system was. In design, we don't care about the initial state of our system. But for engineers, you'd probably want to know by just looking at or by knowing your inputs of your system, can you tell what the initial state of the system was? For example, if I walk into a car, can I tell what gear the car was before I walked in? If I find it in neutral, for example, it would be difficult for me to tell what the initial gear was. But if I find somebody has engaged gear 2, then I'll definitely know that initially the gear was at gear 1, and that's why now it is at 2. So I'm only observing the inputs, but I can tell. Some people can even tell the nature of the gear by looking at how fast your car is moving. So the input could be the speed, but that can tell me the initial state of the car. I can tell the previous speed range by looking at your current speed. Okay, just being able to observe or understand how your system operates. But for controllability, you actually need it in design, because now you are looking at your control input and you're trying to ensure that whichever control input you have, it can be transferred to any state of the system over an interval of time or a finite period of time. Anyway, that is it. I'll leave the rest to your revision. Let me go back to there's another question on the chat. I want to go to the exam and then I end it there. Looks like students are more interested in the exam than anything else, but we don't really teach you for the exams. I wish maybe they would even, discard this examination thing and we just study and continuously assess one another. Anyway, so your exam, typically, I like setting 4 questions for your exams, where the first question is compulsory. But because the first question is compulsory, it has the highest number of marks, which is 30. And so what I usually do is I ensure that the first question contains, or at least tests you on everything that we have done, but only in bits, like just not in depth, just a bit of everything. So we'll do a question on root lockers. We'll do a question on state space representation, because that's basically what we have done, modeling in the time domain and also in the frequency domain. So you will have a question on root lockers. You'll also have a question on states, or questions on root lockers and questions on state space, but not in-depth questions. When I say in-depth, I mean the questions would not be of so many marks. They're just a few marks here and there, because you need to explain a few things here and there, sketch a few things there, mention a few things. So those ones are just typical questions to test whether you understand the concept. However, the rest of the questions, question 2, question 3, and question 4 are very detailed. Those require you to go in depth into analyzing systems properly. So what I usually do, because I know some students would prefer certain topics over the other, to moderate the paper, question 2 is purely on root lockers. And when I say root lockers, I mean everything from initial discussion of what root lockers is all the way to design. That is question 2, but it's purely on root lockers. it's an optional question. Because question 1 has a little bit of everything, but it is mandatory. Question 2 is purely on root locus and the design using root locus techniques, but it's detailed and it's optional. You can leave it or you can do it. At the end of the day, you still have to attempt question 1 and 2 more. So a total of 3 questions for 70 marks. 30 marks from the first question, 20 from the other 2. Okay, that's 70 because you've done your CAT. Question 3 is now on state space. Again, detailed discussion on state space from the introduction all the way to the design. Okay, and question 4 is again everything that we have done all the way, because the question 2, 3, and 4 are optional. So it's testing all those things in between that I have not asked in the first 3 questions. So it's just making sure that we've covered or we've tested all the topics that we have covered, which are basically state space representation and root locus, of course, with their designs. But now question 2, 3, and 4 are very, very detailed questions, and they're design questions. Question 1 has nothing about design. It's all just trying to give me a few things here, mention a few things there, define a few things here. So usually that's just to test the skill, to test the concepts. But now, how can you apply those concepts in a design environment? So that's where question 2 is on root locus, question 3 is on state space, and question 4 is also just a combination of a little bit of design all over the place. Okay, so I wouldn't encourage you to not study a certain topic or a certain area. Please study every area, because that's how you have a holistic view. Plus, don't study with the exams in mind. Study to simply understand this concept so that it goes beyond the exam. Whether or not you encounter it in the exam, you might encounter it in your career path. So please just have a proper, especially when it comes to this design, you will notice that you will apply a lot of this. I usually get surprised when I get a lot of emails from previous students who simply write me emails and tell me, now I understand what you are telling us, because I've met it actually in the industry. And the industry might be unforgiving because they don't expect to train you again on it. They expect you to simply understand it. So once you have the concept, it's quick, it's easy for you to simply connect it to the real life or practical applications, and then life becomes a little bit easy. But if you ignored it, you never studied it because you never wanted to do it in the exam, and then you meet it in the industry, then you become stranded again, and you'll be wishing you actually took time to study the concept. So I encourage you guys, study everything, gives you easy time to even select what questions you want to do in the exam, because you have a pool of questions and you can leave one question out. So it's easy to pick which one to leave out, the one that you're not very comfortable with. But at least you've equipped yourself with the knowledge of a little bit of everything. That's why question 1 tests a little bit of everything. Okay? Any other questions? I don't want, ladies and gentlemen, for the integrity of your exams, I don't want to reveal what I have said, but at least I've told you exactly how the questions are structured and which ones are optional. But you can be sure that we have covered everything that is in the exam. Nothing is going to be strange. That I can guarantee you. All right. Any other questions, ladies and gentlemen, before we close up, because we have about 15 minutes. I don't want to stretch it too much. Anyway, you guys know how to reach me. A lot of you have been sending me emails of when they are stuck in certain revision questions and stuff like that. And I usually try and respond as soon as I can. So you can always do that. I still have no problem up until the time you do your exams. You can always reach out via email or through your class rep on certain areas that you feel you still need an explanation. I'll be available to assist as much as possible. Anyway, guys, thank you so much. I really like that in this class, it's one of those classes that I'm proud of in terms of attendance. You've really tried throughout the semester to attend the online classes. I really appreciate that, and you'll also appreciate it in the second semester, because the second semester will be dealing a lot with industrial automation, and it's on PLCs, programmable logic controllers. And the thing with that is a lot of it needs us to be online for me to actually showcase certain designs so that you can quickly understand them. I might not be able to draw them in class. They are very complex to draw, but if I show you or if I show you my screen and we scroll through the softwares, it will be easy to understand. But because you attend classes in large numbers, it helps a lot, because then it makes me know that you're committed to learning some of these concepts. So thank you guys so much for trying as much as possible to attend these classes. And I wish and I hope this translates into a good performance in your exams. I am not a sadist, so I don't teach you to try and show you that I'm better than you. I am not. I'm actually learning from students a lot. And so I expect that you do the very best that you can in your exams, and you should be able to pass. I don't look to fail anyone unless I have no option. Because if somebody writes for me their name and then attempts question 1A and then leaves everything else blank, there's no way I can harvest marks for you. So, but if I see that you've really made effort to explain certain concepts the best way you know how, and you've solved them the best way you had them from class, you should be able to pass your exams and use that knowledge later in life. All right, so if there are no any other questions, I will end the class here. Thank you guys so much. I wish you the very best in your exams. If possible, I will pop in during your exams to just see if there are any queries, but only for a few minutes, because I'm not allowed to be in the exam room. Maybe I can increase the tension. So I'll try and just pop in to see if there are any queries, and then I let you be and sit your exams in peace. So thank you guys so much. See you around, and reach me out on email if you need to. Okay. Have a good day. Goodbye.